Yeah, we're past the time anyway. Yeah. Hello, everyone. Yeah, this is the plenary session. The second plenary session will start with a talk by Dr. David Wiese from Jet Propulsion Laboratory, who's going to be talking about tracking time variations in Earth's geopotential, past, present, and future. It's going to be 30 minutes, and then we're going to go on to discuss for an hour about the state of the profession.
Great, thanks. It's a pleasure to be here. So the organizing committee just gave me one direction. It was to bring you all back down to earth. So that's what I plan to do today. My name's David Wiese. I'm at JPL. I'm the deputy project scientist for the upcoming GRACE continuity mission. I want to talk about tracking time variations in the Earth's geopotential. And the story starts way before 2002 when GRACE launched, but I'm going to omit that for the sake of brevity, and we're going to start when GRACE launched. GRACE was the first in a series of what should be 3 or more missions. It lasted for 15 years. Design lifetime was 5 years, so it well outlasted its design lifetime. And it was the first mission that really tracked time variations in the Earth's geopotential at a spatial scale that we could really infer quite a bit of science with. It had a link between the two satellites. It measures distance change between the two satellites. It used a microwave ranging interferometer to do that, and it would measure that to about a micron level precision. So GRACE follow-on launched in 2018. There was a 1-year gap between the two missions, and it's a follow-on mission, as the name implies. It's mostly the same architecture as GRACE. But it did have a LRI, laser ranging interferometer tech demo, that improved the ranging precision by down to about a nanometer level, so 2 to 3 orders of magnitude. And GRACE continuity is the next mission we're building. It's a NASA DLR mission. It is also a continuity mission, and it has dropped the microwave in favor of the laser, and it'll have a redundant laser ranging interferometer. So before I jump in, I want to recognize Dr. Byron Tapley. He was the GRACE principal investigator. He passed away earlier this week. He made really remarkable contributions, a true pioneer in this field. And you know, he laid the foundation of everything that you'll see here today. Okay, so this is what we call the postage stamp plot, and we're up to, I think, 257 monthly gravity fields, so each one of them is represented here, and you can see science with your eyes here. There's a few gaps in the data, but more or less it's continuous. We're almost at a quarter century of measurements, which is absolutely remarkable. The data have been taken up by a wide variety of users and applications, end users. We have over 6,000 publications. To put that in perspective with astrophysics, we compared this to Hubble, and over the same amount, Hubble had about 10, 11, so we're about half of Hubble, but it's pretty prolific. It's the second most cited NASA instrument in the IPCC AR6 report, and then terrestrial water storage recently became an essential climate variable, and it contributes to about a quarter of the other essential climate variables. So the reach is wide. What I find most impressive, this is a bar chart of publications over time. The orange is the derivative. So as the time series lengthens, the rate at which papers are being published is actually increasing over time. So it's about 10 per week now. Lots of use cases, and those use cases are all right here. This is an image we generated from the last decadal when mass change was recommended as a designated observable. The observable cuts across these 3 different panels, so climate variability and change, hydrological water resources, and then Earth's surface interior. So I'm going to go through and kind of give a little bit of a highlight reel of some of the things that we've learned from GRACE. And we'll start with the ice sheets. And so this is, let's see if the animations play. Yes, it does. So this is an animation of Greenland and Antarctica. Greenland, on average, has been losing mass at about 265 gigatons per year. Antarctica, about 135. And so we can see the mass evolving over time. It's not a continuous straight line. Some years we lose more than others. And we now know that Greenland mass loss is mostly driven by atmospheric warming, surface processes. Antarctica is a completely different story. It's mostly about the ocean warming and melting away the ice and chipping away underneath. And Antarctica is a little bit of a bipolar story. So we have a spatial allocation of mass, And in Western Antarctica, right here, this is the largest gravitational change on our planet right now. That's Pine Island and Thwaites glaciers. They're losing mass at a remarkable rate. And these mass losses are really being offset in part by some pretty tremendous mass gains in Eastern Antarctica. So you can see we get a pretty coarse picture. The spatial resolution is around 300 kilometers. And so I want to have a quick, let's see, there we go. A little bit of future work we're working on is we're working on combining gravimetry observations with other geodetic observations of height change over the ice sheet. And we're able to improve the spatial resolution of these monthly changes somewhere between 10 to 10,000 times. So I think this is going to be a real game changer for the field. And I just wanted to tease that as something that the community is working on. Okay, how much is a gigaton? This is 1 gigaton over Manhattan. It's a pretty big ice cube. In all, we're losing about 700 of these every year from the ice sheets and the glaciers. The ice sheets are a little more than half, and the land-based glaciers, Alaska, Patagonia, Canadian Arctic, make up the remainder of that. It's hard for me to visualize this. It's much easier for me to think in frozen Mini Coopers. And so it's about 2,500 per second if I've done the math correctly and approximations. Okay, so let's move. So the ice melts, most of it ends up in the ocean. And so this is another major contributor for gravity observations. We have a series of satellite altimeter missions. The latest is Sentinel-6B. That's measuring the height of the ocean over time, and that's the red curve right here. And what we get with GRACE is the ocean mass change, so that mass input into the ocean, which is the green curve. So in ocean mass, the seas are rising about 2 millimeters per year due to ocean mass change, and the total rise is about 4 millimeters per year. So that difference is made up by warming, thermal expansion of the water. So as the water warms, it expands and it causes some sea level rise. And so that measurement right there tells us actually how much heat the ocean is taking up. And so to the extent that our planet is out of balance in terms of energy imbalance, the ocean absorbs 90% of that excess heat. So these two observing systems over this collection of satellite observations and missions represent our best estimate and knowledge of the Earth's energy imbalance, which is about 0.5 watts per meter squared. Okay, so let's move on to water, so groundwater. So we uniquely measure groundwater changes where really no other observation can, except going to a well and dropping a stick down there and seeing how far the water levels are. These are a couple of my favorite papers. This one in the top right, this came out several years ago now by Matt Riddell in Nature, and it was looking at emerging trends coming out of the GRACE data in freshwater availability. And so you can think the reds are the water have-nots and the blues are the water haves. And so there was some source attribution due to climate change or human impact or natural variability. And there's human fingerprints all over this map, mostly in terms of groundwater change. So pumping out groundwater quicker than what it's being replenished into the system. And this has gotten a lot of attention. The state of California actually recently adopted our data into their decisional framework for groundwater allocation for irrigation. So that was a big success story for us in terms of societal applications. This paper on the left by Chandakapur et al. In 2025 came out in Science Advances, and it chunked the data into these 5-year time spans and found the emergence of what they called mega drying zones. And so the continents they found are losing water at a pretty record pace. The dry areas are expanding by about 2 times the state of California per year, and about 68% of those changes are groundwater. And most of the world's population lives in those dry regions. So that has implications for the food, water, energy nexus. Okay, and another application use case is drought monitoring. Our data are operationally assimilated along with other data sources into an operational drought monitor. So this gets updated every week. Actually, a new map came out this morning, but I didn't update it, but this is from last week. And so it maps drought and monitors drought over the world. So one of the signals we're looking at and monitoring right now is this in Colorado. Colorado had a historic snow drought. And this is the headwaters of the Colorado River, which feeds a lot of irrigation and use cases down California, Nevada, et cetera. And so that's going to be a hot topic this summer. So global water cycle. We're able to map changes in the global water cycle. This is an image. It came from, again, Matt had a paper in 2023. These bubbles are exploding. The red bubbles are extreme drought events, and the blue bubbles are extreme flood events or pluvials, and the size of the bubble corresponds to the intensity of the event. And they correlated intensity of these events to global temperature and found a positive correlation. So as our Earth is warming up and the energy imbalance is increasing, with time, actually the size of these events is increasing over time as well. And so this really relates to real world on the ground problems that affect people every day. Okay, so how does the system work? So that was the science. Now I'm going to go more into the engineering. Most Earth satellites look at the ground. We're a lot like LISA. So there's 2 satellites. They're about 220 kilometers apart at a 500-kilometer orbit. The orbit naturally free falls. As the lead satellite approaches a mass anomaly, it speeds up relative to the trailing satellite, and then the trailing satellite will come and speed up. And they're doing this dance, this tango as they orbit the Earth. And it's those tiny changes in distance that we're able to measure and map and then infer the water, how water is cycling beneath our planet due to those distance change measurements. And yeah, this is an animation kind of showing that cycling of water over the Earth. And so this will zoom in a little bit. We're going to pop off the solar panels to show you the main instruments that are used. Here on the front, this is the K-band microwave ranging instrument that's on Grace follow-on. And then this is the laser tech demo. So there's 2 beams. There's a triple mirror assembly where the laser light is routed around, but there's a vertex at the center of mass. We have a precise accelerometer that resides at the center of mass of the spacecraft. And then we have 3 star cameras for attitude control or attitude knowledge, orientation, and then a GNSS antenna for inertial positioning. The GNSS actually provides very critical information for the largest mass change features that we estimate. And the star cameras are also very important for the attitude, I should say, is very important. So you are the only audience that will probably yawn and get bored at this slide because of the analogies that we have. But the point of this slide is we always say the spacecraft is the instrument. What we really care about is tracking the center of mass between these 2 spacecraft, these 2 bodies, and we've built the spacecraft around it. We're not ranging directly to the accelerometer or to the proof mass like LISA is, but our ranging measurement, the LRI is designed so that the vertex of the triple mirror assembly is very close to the center of mass. But we need to control the center of mass over the life of the mission to within about 100 microns. So there's 2 fuel tanks. We try to draw from these fuel tanks at the same rate so the mass distribution doesn't shift, but inevitably there's a little bit of a leak. So we have these mass trim mechanisms where we'll do calibration maneuvers, see how the center of mass is migrating, and then we will trim the mass to keep the center of mass of the satellite flying around the proof mass to within this 100 micron level. Okay, so data acquisition. We get about 15 orbits per day at our altitude, so the coverage is reasonably sparse over one day. It fills in pretty well over a couple of months. We can estimate like a 2-weekly gravity field. It's just not as good in terms of spatial resolution. And then over a month, we have very dense coverage. So this is kind of a sweet spot that we've converged on in terms of producing our data products. And so here's one slide on how to estimate a gravity field, which is kind of like the global fit. I loved the talk yesterday. There's a lot of similarities. But this cartoon is supposed to be, the red are our observations. So these are our range rate observations, our GNSS observations. And then we have a prediction. We predict what we think those observations should be. And those predictions, we would say, are given by the blue. We have a predicted orbit, and then we can simulate what we think those measurements should be. And then we want to minimize the difference between our predictions and our observations. The prediction, we use very high fidelity force models to predict where we think we are. The one thing we don't include are the hydrological mass variations, because any difference between our observations and our prediction, that's our residual, that's the hydrology. And that's what we are estimating. We do a large least squares estimation problem where x is our vector of unknowns. It's somewhere between 10 to 40,000 gravity field parameters each month that we estimate. We have a matrix of partial derivatives that relate the observations we take to our state parameters, and then we can also include prior information if we want to. So I will point out on this slide, these high-frequency mass variations, models of high-frequency mass variations, ocean tides, and the non-tidal atmosphere and ocean mass variations that occur on hourly timescales. To the extent those models are wrong, that's currently our limiting source of error, okay? And I'll come back to that. So this is also kind of a global fit problem. If we just let the data go into the problem, we end up with a map like this on the left. Since we're in our observation geometry is purely north-south, if there's an east-west gradient or mass variation, we are kind of insensitive to it. If you look at the covariance matrix, that's what I call, those are the holes in the armor. So all of our error ends up going into those holes. Those holes are longitudinal stripes. So there's a whole cottage industry that's been developed on getting rid of those stripes. So we're de-striping this, de-striping that, and then smoothing, and it's been pretty good. Alternately, we can go back to Bayes' theorem and bring in external information into our problem when we do the gravity solution. And when we do that, we have these constrained mass solutions, and we can kind of get rid of those stripes inherently. And that's been an advancement in the last several years within the community. Okay, so we've got this data record. How do we build upon this data record? We're going to go forward-looking now. And so this, the community has discussed this. So the first priority is continuing the data record. That's grace continuity. And the second priority is to really improve the data record. And when we improve, we need to think about what we're improving. And so we have to think of the quality of the data products really in these three dimensions. It's temporal resolution, spatial resolution, and then accuracy. How accurate are those estimates? And so there's been so I want to ask, how can we improve this in terms of a mission design? You want to design a mission to improve upon what we're doing. There's been a lot of study on this in the international community. I did my PhD on this. This is kind of how I got started in this. And I could talk the whole time about this, but really there's three things you can do. Number one, we can lower the altitude. You fly closer to the source, so your signal-to-noise ratio increases. Number two, we can add directionality to the observable. So imagine if you sample something in the east-west or radial direction, you're going to get rid of those stripes we were talking about. And then number three, we can increase the sampling frequency. So remember we said our models, these high-frequency mass variation models, that's our limiting source of error. So why model them? Let's just measure them. So let's measure them. And you can do quite a bit doing that. And so, Pete Bender, this is where Pete Bender comes in from day one to now day 4 in Nora's talk. So he also has had an impact in our field, and he had this paper in 2008 recommending a polar pair with a 63-degree inclined pair. We now call that the Bender. That's actually what, and so I would, Pete and I would go back and forth, but Pete said 63, I say 72. It's somewhere in there. I think it's closer to 72. But Pete's general idea was the right one, and so this is what the community has locked onto. And now I really want to go full circle. I'll tell you a tiny story. So Pete passed away in 2024. He had a final manuscript under review at that time, and he had some revisions that had come back, and it was really on the importance of flying an improved accelerometer on a satellite gravimetry mission and resolving short period mass fluctuations. So Pete's son reached out to John Conklin, and then John reached out to me and said, can we finish this paper? And so we did as little as we could to the paper while addressing the reviewers' comments. And so if you're interested in reading Pete's final hurrah, it's in JGR Solid Earth. You can go check it out. It's about accelerometers and short period mass variations. Okay, so going back to also future looking. So the last decadal for Earth science recommended mass change as a designated observable, which means it's one of the most important things we should observe over the next decade. NASA stood up some study teams to look at that. And so what we did was we developed a science and applications traceability matrix. We identified a whole ton of architectures, different architectures that could observe mass change. We assessed those architectures very rigorously with numerical simulations. Then we mapped the science value. We derived a science value from those architecture assessments and mapped it back to the decadal. And so this is in one slide kind of the outcome of that study. So What we're mapping here is science value versus cost. Science value on the y-axis, a value of 1. If you're not above 1, it's not worth doing. So 1 is basically continuity with the program of record. That establishes the minimum bar. Value of 4 means you have about a 4x improvement. What does that mean? It's some combination of spatial resolution, temporal resolution, accuracy. You're doing about 4 times better. We could go into a lot more detail there, but this is what decision makers like to see. So we pruned the trade space, and we ended up with about 10 high-value observing system architectures that also partners were interested in, et cetera. And so the outcome of that was this architecture A1. This is now the joint effort by NASA DLR. This is Grace continuity. It's going to be a polar pair of satellites, 500-kilometer orbit. We're currently in phase D. We're marching along, making great progress, no showstoppers. We're going to launch in December 2028. It's looking really good. This architecture D3, this is the combination of the Grace continuity mission with another pair of satellites. So this makes a Bender formation. And so ESA is leading the development of that pair of satellites. It's called Next Generation Gravity Mission. They're going to fly at 400 kilometers altitude, so it's lower. They're going to go inclined at 70 degrees. And since they're lower, they're going to have drag compensation. You have to in order to not deorbit very quickly because the atmosphere is pretty dense there. They're currently in phase B2, and they plan to launch in 2032. So the combination of those 2 satellites, they can be operated completely independently, and we can just combine the data on the ground to get these improvements. And so we expect about a 4 times improvement in science value when we do this. Okay, so let me check the time. Okay, so the story doesn't quite stop here. A couple of more things to mention. So this plot on the left here, this is what we call a degree variance plot, and not to get into a lot of detail on it, but these bars each represent the quality of subsequent data releases. And as they go down, we're improving. So since the very first GRACE data release till now, we've improved things by over an order of magnitude. So we get those improvements in being more clever in how we process the data and also having those force models improve. So better tide models, better models of ocean dynamics and atmosphere moving through the system. There will be a point in which we hit a floor on improvements, and that floor is driven by how good the measurement system is. So how good is our accelerometer and our ranging measurements? For GRACE C, the accelerometer will be the limiting source of error in our measurement system. So it's the laser range interferometer is about 2 times better than the accelerometer if you map it to geoid or geopotential change. And so that leads me to a couple of ongoing upcoming activities. So this Gratis mission is going to launch. NASA ESTO has funded it. It's a technology demonstration of 2 high-precision accelerometer technologies. It's going to fly a simplified gravitational reference sensor led out of the University of Florida, and a secondary payload, the Odin sensor, which is a combination of optomechanical inertial sensors led by University of Arizona. Felipe has a poster on Odin this afternoon, and then Peter had a talk on Monday on the Gratis mission. So you can go back and watch that, from the recordings if you're interested. Mission success is to meet the GRACE C requirement. The goal is to do 10 times better. And there's really no showstopper if you put this on a drag-free platform or drag-compensated platform to get down below 10 to the minus 12. And that's kind of what Pete was advocating for in his paper. There's another activity. So this was the slide I showed you earlier, and I didn't focus on these yellow bars. But this is a quantum gravity gradiometer. So if we have a really precise quantum gravity gradiometer, that's about 1 e to the minus 5 etvos. We have potential to measure these gravity changes about as good as we can with these 4 satellites, these 2 pairs. We can do that on a single satellite platform. So NASA has funded, or they are funding, a quantum gravity gradiometer pathfinder mission to reduce risk for future science grade implementations, planned to launch in 2030. It's going to fly the first quantum sensor that's capable of measuring the Earth's static gravity field. So that's an important distinction. So this is like 1 e to the minus 1 etvos sensitivity. So there's still a 4 order magnitude gap between the pathfinder and then what we would need for what we would call a science-grade implementation to measure mass change. But this is really important for reducing future risk. And Ben Stray has a paper in last year on this. Okay, so I'll end here. So, I like to end looking forward. So, soon we're going to have 3 decades of continuous mass change measurements. It's a real Earth climate data record that spans many applications. We hope to have this operational observational system that's about 4 times better than what we're doing currently. And we're also working on improving technologies, accelerometer technologies, and demonstrating the first quantum measurement of Earth's gravity field in space. So these are going to continue to be prolific and generate a lot of new science and applications. So I'll end here. Thanks.
Thank you for the excellent talk. Are there any questions?
So thanks a lot. My question is whether there might be some overlap between GRACE follow-on and GRACE C, and if so, is this going to give us some information about how much we gain going to 2 pairs?
Yeah, absolutely. We're planning for overlap. That's one of our driving design principles is once GRACE C launches, we'll be delivering gravity fields with combining the data from both pairs of satellites. What can we do with it? Having 2 polar pairs is not nearly as valuable as having a polar pair and a lower inclined pair. So to first order, what we can do is make a 2-weekly gravity field, like a gravity field at the same quality as GRACE every 2 weeks. So we can definitely improve temporal resolution by a factor of 2. In terms of spatial resolution, you get about a 10% improvement with 2 polar pairs. And it's because of the stripes. You haven't shored up your covariance matrix like you can with a lower inclined pair. But yeah, and so we might even have 3 pairs if GRACE follow-on keeps working and GGM launches, but that, I don't want to get too ambitious.
Yeah, hi David, thank you, that was great. I'm gonna go off to the side a bit. I want to ask you something about science communication because, as I'm sure you know, this is a hugely charged topic when it shouldn't be, right? But one of the things that you said, which is something we do a lot in science, is we say, we constantly work on our data, we improve what we did, we're more clever, and now we have this better result. And that makes some people's heads explode. Mm-hmm. And so I like to ask my colleagues, how do you respond to that question when you get it from someone who's not trained like we are? What do you tell them about that process, and how do you explain it?
That is a great question.
If you don't know, that's fine, but I always ask because I think it's helpful to hear how all of us approach it so we can work on this.
Yeah, I think, you're going to have this problem with the global fit. I don't know if I have a really good answer. Yeah, I think it's a challenge, and I think it's just, I think trust is a big piece. Having people trust, and so being honest in communications, I always feel like it's better to be honest in communications. That kind of builds the foundation from which we can build upon. But having them trust that, yes, the first time you're going to do this, it's not going to be the best, and then over time, it's going to get better. Yeah.
Another question here. Thanks for the nice talk. Yeah, I guess I was wondering, if I remember right, the original GRACE was microwave interferometry,
yes.
And then switched to lasers, right? And I just wanted to know if you comment on how the ranging improved and about the phase meters. Would they be good enough for gravitational waves as is, or is there something different in the design?
Yeah, I don't know if they're good enough for gravitational waves. Someone brought this up recently, and I'm guessing not because someone would have done it, but I would, if you could show that as the community, that would help us out a whole lot. That would be pretty cool. The precision increased from the microwave to from the microwave to the laser by about 100x, and so there are everything I showed here. We don't see a direct improvement in our gravity fields processing the laser from the microwave because it's not our limiting error source, but there are some cool, innovative ways of looking at the data that some people in our science community are doing, where they do this, what they call a long track analysis, where you would fly over a mass anomaly, and now since your noise is significantly less, you can potentially solve for a mass anomaly directly, as you overfly it. Kind of a different way of looking at it. The problem is it's not a unique solution when you do that. There's a lot of different mass variations that can explain a wiggle, but you can do something with it. Yeah.
Do we have any questions online? No. Any last question?
Hi, that was super interesting, thanks. I was wondering what went into that regularization term to control that huge dimensional fit that you did, and
Yeah.
Was it very fine-tuned, or what kind of physics went in there?
Yeah, pretty fine-tuned. So we changed the basis function from spherical harmonics to mascons, and mascons are you can think of them as tiles covering the Earth, and it's reasonably straightforward. There's several different ways you can do it. The way we do it at JPL, or the way that we developed, is that we use a set of models. So an ocean model, a hydrology model. Other places where we don't have good models, we leave things unconstrained, but we get expected variance from those models, and we put that in as a diagonal constraint on expected variance in this mascon should be this. And we have off diagonals the same way. How correlated do we expect these mascons to be relative to one another? And we implement it. There's a lot of other nuances there where when, like the large mass variation in Pine Island and Thwaites, it's growing, it's getting massive. So you have to let your variance, expected variance, be really big because it's a big mass change. So what we have also done is implement a Kalman filter. So we do a time correlation going forward and backwards in time and smooth it. And so like every month we produce a new solution. We're actually re-delivering the entire 24-year data record. And that's because this new month has actually given us a little bit more information that helps us with everything. Maybe counterintuitive, but that's how a Kalman filter works. And it helps us resolve those trends. Yeah.
Cool, thanks.
Please join me in thanking the speaker again. So now we're going to have a set of talks that are going to preface a panel discussion on the state of the profession. Yeah. Hontas. Okay. Yeah. Yeah. Can we have the rest of the panel up, actually?
Good afternoon, everyone. Is this working? Good afternoon, everyone. My name is Hontas Farmer of Chicago State University, the only primarily black institution in the great state of Illinois. And we're going to talk about DEI. Those can be dangerous things to put together. If the clicker will work. Am I pointing in the wrong direction? Yeah, down. Okay, here we go. Thanks to everyone who agreed to speak. If I speak, I am in big trouble. So I totally get it. Unfortunately, the sound didn't play, but you've all seen this meme if you're under a certain age. So thanks to the three who have agreed to give extended talks here. We're also going to have panelists, and I placed, and volunteers very graciously placed, index cards by your tables. If you want to write down a question or comment, we will go through them, or if there is something you want to share, but maybe you don't want it to be public. If you're online, I believe they set up a word cloud for you to comment as well. And if you're brave, you can go ahead and grab a microphone and ask your question, okay? So first talk is going to be by me. I'm going to be talking very fast because there's a lot of basic facts to get through. Kelly Bockelman is going to have a talk. be a bit of a choose our own adventure. And Paula Delgado, who is a remote participant, will be talking about issues that affect people who had to travel from one continent to the other, one country to the other in order to work on LISA. Okay. And Ricardo Wabel will be on the panel as well. So the problem with this issue is it can be very specific to a particular country. Here in the United States, for us, you know, you think of the Black civil rights struggle, right? And people think DEI means unqualified people getting advantages they don't deserve. It wasn't random where I put this arrow coming from. Like me, this guy, Malcolm X, his family was from Omaha, and that's where that is. DEI can have a certain connotation in history in a given country, but in a global context, it's more complicated. We're talking about improving working conditions for a diverse set of people who are qualified, but who might still experience inequities and exclusion. Now, I mention this because in a global context, African Americans like me are actually somewhat privileged. We are the oppressed group in American history, us and Native Americans, of course, you know, you probably, even if I didn't tell you his name, good chance you knew who he was, right? And since emancipation, we've had some degree of influence, and we are also part of a global superpower, right? We earn dollars. That means that we have money. Diversity, equity, and inclusion in general, and also, you know, we have a pretty good passport as well. We're going to talk about that. Basically, this is the definition of DEI that we came up with. It's a commitment to ensuring that all people are treated with individual dignity, guided by the principles of openness, fairness, cooperation, respect for human rights. And I find that you know you're seeing DEI in action when a large group of people agree to embrace the differences between members of the group in a way that accounts for pre-existing imbalances. That's when you're seeing DEI in action. So who are we and what do we do? How did we get to be on the DEI committee? Basically, we were nominated by other people for the role, and there's never been a number of people such that some sort of wider election was necessary. We do things like demographic research and things of that nature. So there's a consortium-wide call for nominations. These are the current members. If you are in the room and would like to stand up and be recognized, any of you? I guess not. Like I said, it can be dangerous, right? So how did I get to be on the DEI committee? How did we get to be on the DEI committee? Basically, in actual practice, it comes down to the chair people of the group doing things like this and trying to encourage people to get on the committee. The best analogy I can think of actually is the way this gentleman from Chicago became the Pope. The previous Pope, Pope Francis there, he decided to diversify the Catholic Church's leadership. And he tried to find people who were sort of hiding in corners of the church who usually didn't get to be cardinals, and made a whole bunch of cardinals who were sort of outside the usual power structure. And now we have Pope Leo, who is carrying on that same tradition. So we lead the consortium's DEI efforts. We monitor and review the health of the consortium in DEI terms. We plan demographic surveys, and our work is structural. It's about how the consortium functions, not individual grievances, though if you have individual grievances and bring them to us, we might be able to help you. So the scope of our work, not just surveys, we also help the council review policies. We are either voting or ex officio members of various other groups like Appointments and Elections, LEX, Communications. So we are deeply integrated into all of the governance of the council, and we can make recommendations about what to do to improve the DEI efforts. It has to connect evidence, governance, and practical access. Otherwise, it's just a meaningless rubber stamp, right? So just to sort of get through all of this a little more quickly so other people will have a chance to talk, if there's one thing you take away from this, the closest thing I could come up with to a law of physics for DEI is this. If you have a slate of candidates for leadership, and you want leadership that is as diverse as that slate of candidates, or even, then you need to have the candidate slate be more diverse than the leadership you see. It's not enough to look at the current state of leadership or the current demographics of the consortium and say, this is as diverse as we are, and we're just going to preserve that because there are some issues where we could do better. So the 2026 demographic survey found the following: 677 respondents. Come on, go forward. There we go. Respondents, we're highly trained, highly qualified people, so we're not talking about giving opportunities to people that don't deserve them. 67.8% are core members. We also have the community members as well. And astrophysics and cosmology are our most active working groups. Representation, 71% men, 26% women, 2.6% non-binary, and 11.8% of us, which is larger than the general population, identify as LGBTQ in some way, and 5.1% reported disability. So we're very diverse in the bulk sense of the word, yes? 10.7% report discrimination in their country of residence. Okay, so even if you are not being discriminated against within LISA, you might have conditions you're working in outside of LISA that affect how you can work for us, yes? So now, talking about race is something that is very hard to do because it's a bit of a social construct, right? So we went with what continent do your ancestors come from? As in, where were your ancestors mostly when there was an ice age the last time around, right? And mostly that's Western Europe. Eastern Europe, East Asia, South Asia, not many from sub-Saharan Africa, which is interesting. For most of us, English is a language spoken at home as a child, but there are many, many other languages as well. No, wait a second. 48% were Caucasian, only 20.5% spoke English as a child, so yeah, just the opposite. Only 24.5%, so about a quarter, don't work in the same continent as you were born in. And in terms of country of birth, roughly half of us had to change countries. So immigration and travel issues are of concern. The largest country in terms of number of people are Italy, actually. Yeah, I noticed this just by seeing the very many faces and names. We are a very Italian collaboration, 11% or so. Hey, so is Chicago, I'm used to it. 11% from the USA, followed by France, Spain, the UK, Germany, mostly residing in Italy. 15% live in the USA versus originating from the USA. And cross-border relocation is the norm for nearly half of our workforce. In terms of gender identity, let's see, are you a minority which does suffer discrimination by law? Gender identity discrimination, 26.7% have faced discrimination by law. Women and men as well. Now this is not broken down because that could include also some trans women and trans men in women and men as well. Disability, yes, in terms of discrimination, so 22.7% reported yes. Now these don't add to 100 because not everyone answered every question. Now let me cut to the chase a little bit. Probably the biggest sticking point has to do with leadership. Europe pays about 80% of the bill and has a bit of a echo over there, 80% of the bill and gets about 77% of the leadership. The Americas altogether, so US, Canada, Brazil, all of the Americas put together, you get 15.9%. Other regions get 6.8% of the leadership. Now, something that is a sticking point here is you see America, the United States, is paying 20% of the bill, but only getting 15.9% of leadership. LISA countries and people from those countries need to consider trying to find more people from non-LISA countries to be involved in the leadership. That's pretty much what I'm saying with this, by about 3%. For example, people like our colleague from China might be a good addition if you can do that. So concentration within regions. We see that concentration within regions and institutionals is not that bad. The largest institutional affiliation we could find was none or unknown in terms of people in leadership roles, or maybe they had multiple leadership roles, multiple institutional affiliations, excuse me. Repeated access to formal roles can normalize that only certain people or types of people are worthy of leadership. That's a big problem. One complaint we had on our anonymous feedback form was that leadership in LISA is a bit clubby. It's the same people playing musical chairs all the time, and we want to make sure that that's not the case. So now here's the main event, concerns. It's not enough for the DEI committee when we're doing our work to just count members and then say, oh, this is as diverse as the consortium or as diverse as leadership is. We have to try to slightly make people in leadership uncomfortable and ask you to reach outside your usual networks. To do this, we need individual level data about your candidate slates in order to even make these calls, okay? If you're a candidate for leadership, I'm a very minor politician in Illinois, very minor. And the thing about running for any kind of office is people are gonna know who you are. So share what you feel you are comfortable with and get comfortable with the idea that people will know, hey, you're a woman of color from a certain country, or you're a Caucasian male from a certain country who happens to be bisexual or anything of that nature. We keep that information private. We don't publish it, but we do use it to try to assess just how diverse a slate of candidates is. The Rooney Rule. Here's an example from the NFL. They actually make an effort to interview more than one woman and more than one person of color for any position. So they don't have a quota to get X number of people. They just try to interview a large group of people, a diverse set of people, and then they choose who's most diverse from that set of people, and by increasing that probability, you naturally increase diversity without having to say, well, we need to check the box of having a woman or a person of color, right? A&E and DEI working together. So this can be a bit of a pleasure, let's say. It's not enough, like I said, for your working group your working group's selections to be broadly representative. We need to push for more than just broadly, barely representative. Again, I come back to this analogy. You'll find people going to visit the Pope now who are not Catholic because he's somebody from a region that until very recently, and by region I mean all of North and South America, had not had one Pope, even though Latin America in particular has one of the largest Catholic populations. And the United States was almost lost to the Catholic Church. Like, this guy is, especially if you're from Chicago, this guy is insanely popular. You want to reach out to diversify your leadership within LISA, because if somebody is a Lex member, or maybe they're not well engaged with a lot of these networks, they might be someone who could be standing on this stage someday who would have otherwise just left. And we don't want them to leave, because if enough people like that leave, LISA dies. Okay, LISA is not just an instrument, it's all of our interest in being part of this group of people who want to build and understand the world using this instrument. Okay? And we need to make sure that that is a diverse and constantly refreshed group of people. Okay, now, be like Pope Francis, if you are a leader. Like right now, try to find people who you want to have in leadership, make them part of your work, and get them in position so they can go on to do more such work. Okay, I'm going to go a little faster now. I mentioned that already. Think broadly about DEI issues. For example, suppose you're from a country that has noticeable minorities, a very large country. If your government is doing something to those minorities, that could be classified as cultural genocide. Make sure you reach out to those minorities. Make sure that they are involved. Lord knows the United States of America has had to grapple with that issue, as all large countries do. Consider types of minorities who are often forgotten. For example, people who speak regional languages or speak with an accent that people discriminate against. Passport power. This is one I really want to hit. It's not a side issue. If you're from the United States of America, like I am, you have a passport that will let you go anywhere. You have money that people will accept pretty much anywhere, okay? If you're from the EU, and you're from a Schengen country in particular, I hope I said that right, then you have a very powerful economic situation and a very powerful passport as well. Not everyone does. For example, people from India have a hell of a time getting into this country, okay? There are things we can do about that. And one of the big ones is, as much as we try very hard to make participating online equal, one option that I know was considered but rejected for this meeting is something that the IEEE are going to do, or will do if there's enough interest in it. They're going to have a more telepresence accessible sort of setup where they have a satellite conference in Hong Kong, in addition to the one that they're going to have in Bristol in the United Kingdom. So imagine how much more, how many more people could have came if we had maybe that screen over there was showing a room like this that was, say, somewhere in Canada, which is a little easier to get into, or even better yet, somewhere in Europe. So more colleagues from Europe who couldn't afford to travel or couldn't find the time to travel could come, yes? But I understand it's difficult to do that. Also, access to money without fellowships or PI or co-PI opportunities. It can be very hard. Funding cuts, conservative departments, unstable grant shape who can stay in the field. Just speaking about myself, I'm just an adjunct at Chicago State University, but they still expect us to have this on our faculty page. And I've mostly worked at community colleges, so that's not been an expected part of the job, but they've helped me to get some space grant funding to do something gravitational wave related. Maybe I'll tell you about it when it's a bit more mature. Yeah. Early career survival. Well, we have someone on our panel who's going to talk about early career issues. My career isn't early. I'm just, not as advanced as some people. Organization of our connections. That's something that I want to also talk about. One thing we want to do is figure out how to take all the job opportunities and PhD positions we hear about and put them in one place where people can find them, rather than just having them come to your email box and you have to be looking. I'm sure many LEX members would like to know where they're going to find a job that will put food on the table, right? That's the number one thing. You can't stay in physics if you can't feed yourself with it. What I do myself, other than being an adjunct, I also train AI, and lately this summer, mostly, I've been driving Uber. It's not bad. It's not a bad thing to do, but still, shouldn't I be doing research? Concluding remarks. We're not here to make the consortium perform virtue. We're here to make the consortium be virtuous and to live up to all the things in its charter and bylaws. And we're not going to stop at just counting how many members your current leadership team has, and if your slate of candidates is the same as the makeup of that. We want you to do better, and you should want yourself to do better, because every single one of us is here now because somebody in the past thought it would be a good idea that we could add something. So try to find people who are outside the usual networks you think might add. Now, what I've done is I have made you aware of what confronts you in terms of DEI, and it's up to you, especially if you're in leadership, to create your own program for how your working group can best make LISA a better place to live. Come on, clicker. Oh, it's the old-fashioned way. And, again, my favorite Chicagoan right now, the idea of social justice helps us recognize that injustices do not arise solely from the wrong choices of individuals, but also from structures, mechanisms, and economic and cultural systems. And that's what we are building here. And if it turns out to be one that promotes, any sort of discrimination or bigotry in any dimension, it's entirely our fault because we're completely controlled within LISA, and we're also in control of how LISA as a consortium responds to the external forces that affect it. That's my talk. I hope I didn't go on too long and didn't bore you too much.
Hey, folks. Thank you. Thanks. I just have a few, so this is a panel, so I wanted to give you some ideas of things that we could talk about. So this is why we have your cards on the tables and some pens. So if you want to talk about some stuff with us, great. If you're too shy or want to talk about things in person, I'm here until Saturday morning, and you can email me if you are too shy too. Here are some topics I think I can talk about. So I can tell you some tales about how the past year has gone trying to do DEI in a hostile environment. So I have tons of tales, and I'm happy if you all want to share yours too. I think it's good to talk about this. I can also talk about some of the things I've done and worked on that are examples of healthy communities, and that maybe can give us some ideas of initiatives that we could do within the LISA community. So I can show you examples, and I'd love to hear your own if you think something is super helpful that we should implement. And then finally, I have a specific idea for how to build a very healthy consortium. And I can pitch that to you all and beg for help. Not beg, ask for help if you would like to help out. All right, so that's it. And I have plenty of slides to talk about each of those topics, but I'm not going to show you them because they're just to guide the conversation. Okay, thank you. And then our online person.
Okay, our next speaker is remote. Paula Delgado, are you on and ready to go?
Yes, hello Hontas, can you hear me well?
Okay, go ahead. I'll advance the slide when you tell me to.
Okay, so I'll say next, and thanks a lot for the help. So hi everyone, I'm Paula Delgado. I was born in Brazil, and currently I'm working at Seiko in the Czech Republic as a postdoc, and I'm also a member of the LISA DEI committee. During my part of the talk, I would like to discuss with you how science requires diversity, equity, and inclusion, and more particularly, how immigration aspects are an important side of this requirement. So to illustrate, I chose this painting by Tarsila do Amaral, who is a Brazilian artist, where she depicted all of those faces to show the workers that actually built the industrialization of São Paulo. And here we can see many different faces, not only from the immigrants in Brazil that migrated from many different regions, but also immigrants from Lebanon, immigrants from Germany, from Italy, from Syria, from Japan, and who, by the way, are still present in Brazil nowadays. So you see these very fatigued faces because they were treated as a whole single mass of workers and they did not have their diversity acknowledged and they were not heard as individuals. And this is related to many of the aspects that I would like to discuss with you today. Next. So to start with, I would like to just briefly recap what Hontas already very nicely presented. There is why DI matters for an international collaboration. So I believe that here in LISA, we all aim at an international scientific effort to make this mission successful. And we want to gather the experts from all around the world that are very well qualified people to make the scientific development that we all have been working on. And as I'm going to show in a few slides, excellence is reached when experts from the whole world are included and heard. So with the part of the participation that Hontas stressed very well. And here from the demographic data, we see that we do have, as Hontas showed, many different people from different regions of the world, different continents, and we do have some diversity, but we do need to actively work to increase it. And as a step forward, we need to ensure participation with equity and inclusion. And only from the demographic data, we see that race and ethnicity diversity is not a side aspect of LISA. It's one of its defining characteristics. Next. Another very important question is how many of us work outside the country where we were born? And as we have seen, nearly half of us do not work in their birth country, and nearly 1/4 of us do not work in their birth continent. This tells us that our career, the profession we chose, is extremely mobile, and many of us have already migrated. And we are, nearly half of us, formed of immigrants, which sometimes we forget about. Next. And in this data here, we can see the countries where people were originally from, the countries where they reside nowadays. And all of this data that just tells us that immigration is not a side aspect of LISA, it's one of its defining characteristics. Next. So that said, what I would like to discuss with you today is some of the immigration challenges that nearly half of us face, of course, in larger or smaller degree, depending on your nationality, but something that we should think about and we should try to work on in order to make the life of our colleagues or even our own lives easier inside the collaboration so that we can make a better scientific development. So here I would like to focus on 4 of those issues, and here I have a longer list that I would invite you all to carefully take a look and to think about all of those issues that either you or colleagues that you know might be facing. And the first one is the visa and residence uncertainty for many nationalities. So as an example, for many of us, we might even receive an offer to a job in a specific university and might not be able to actually take it because of not being able to get a visa or a residence card in specific countries due to our nationality. We also might have limited access to funding that depends on citizenship or residency status. We also have limited access to conferences, workshops, and even the collaborative meetings due to a difficulty to get a visa to go to certain parts of the world. And on top of all of those governmental and political challenges that we face, we also go through subtle bias, stereotyping, and assumptions about our competence only based on our accent, nationality, race, and ethnicity. Next. And this list shows us that these are structural realities that affect, as we have seen, half of our collaboration members. Next. Second, that scientific participation is shaped by factors outside of scientific ability. And next. Last, that talent is global, but opportunity is not. And we need to think about those aspects in order to make sure that everybody that is involved in LISA has actually the possibility to contribute. Next. So now I would like to talk to you about the more practical side of it, because I hope we are all already convinced that those challenges, they have a real and significant impact on the lives of people that work in LISA, so our colleagues. And to me, this is already enough reason for us to try to work on these issues and help the colleagues that are facing them. But there is even more motivation behind it, because it actually matters for science itself, so for the scientific development of the mission that we are working on. First, because different educational and academic traditions produce different approaches to problems. So we challenge assumptions in a different way, and we avoid blind spots that would be present in a very homogeneous group. The second aspect I would like to focus on is that inclusion improves recruitment and retention of talented people. So we don't want to lose the students, the women, the immigrants that have trouble getting a position due to visa issues, for instance, because they are all very well talented. The next one is that diverse networks expand access to resources. And this is something that I've seen in collaborative projects because in projects within LISA, I have seen, for instance, a cluster that is available to people in one specific country being made available to someone else in another country that is extremely qualified to do some task, to work on something, but simply does not have the access to a cluster, for instance. So this is present in our collaboration. And the last one, which in my opinion is the most important one, is that scientific results gain legitimacy when produced by communities that reflect the global population they serve. So I think we should remind ourselves why we do science, and that we do science for the society and for the scientific progress of the whole humanity, not only for ourselves or for smaller groups. So diversity, equity, and inclusion are not separate from scientific excellence. They actually help to produce it. Next. Now I would like to go back to something that Hontas stressed really well, that DI is about participation and not just representation. So let's start asking ourselves in our collaboration meetings, for instance, who speaks in the meetings, who gets invited into projects, who gets nominated for leadership, who gets remembered when opportunities arise, who feels comfortable asking questions. The demographic data that we have is extremely important because counting people is necessary for us to know whether we have diversity, but understanding participation is a further step that we do need to make. And even a bit beyond the collaboration, like in the communities that we have, it's very useful to ask who benefits and has access to the science and technology that we produce. So here in LISA, we have many people from many different countries, different continents, and do all of those groups, do all of those countries and continents and communities benefit or will benefit from the science and technology that we produce? So this is more of a provocative question that I would like all of you to think a bit about, because human knowledge should be collective. Next. Here I have a list that is not exhaustive, of very small actions that we can take to make the lives of the people that we work with and our minorities a bit easier. So we have very simple tasks that we can take. Here in the individual actions that we can have, I would like to focus on the last point, that is to make space for diversity and be aware of discriminatory biases. So especially when we are hiring people, when we are inviting people to give talks, to visit our institutes, to start collaborative projects, in elections, when we are writing recommendation letters, we should keep in mind that we all have our own internalized biases and we do need to work on them. Next. Finally, in this last list, I would like to give a few actions that institutes and collaborations can do to make the life of our colleagues easier. So I would like to focus on two of them. The first is to consider the visa, caregiving, and accessibility constraints when organizing events. And this also includes assuring that we have high quality remote participation for our colleagues that cannot be present, for instance, due to lack of funding or due to an issue with visa. And also to recognize service, mentoring, and community building contributions. Of course, the scientific contributions are also extremely important, but science cannot be made without the people. So we do need to make sure that everybody is included and heard via the community building contributions. So with this list, I conclude the main thing that I wanted to talk to you about. Before the panel, and I would like to thank Hontas for handling the slides and all of you for listening.
So we're going to open the panel. There, as Kelly mentioned, there's a bunch of pens and papers. If people feel uncomfortable directly asking questions, we know this can be a difficult topic. You can just write them. Otherwise, if you feel comfortable just voicing them out for the panel, feel free. And we'll be collecting them. We might be able to also create a board cloud. We're still working on it. But, you know.
Feel free to ask anything. I am a card-carrying libertarian. Anything you want to say, even if it's a little spicy or embarrassing, feel free to ask. Or if you don't want to be, if you don't want to speak, you can go ahead and just write it on a card. Yes, Shane, can someone get Shane a microphone?
So I can speak to give people time. So, I mean, what you said, Hontas, is absolutely right. This is uncomfortable in the United States. It's particularly uncomfortable and dangerous for various people at the moment. But I think the kind of fundamental problem is we don't often talk enough about this. You know, once every time we meet, once a year, you know, we have an hour-long session, it's enough. But in terms of making progress, you know, Pope Leo's like of the White Sox notwithstanding, what can we do to prioritize the long list of things that we know will help make our community better? There's lots to do. Our workforce is limited, and how do we decide which one of these has the most impact or is the most beneficial thing at the moment? How do we get started when there's so much we could or should or would like to do?
And I'll let the other two panelists answer this as well. I feel that the reason I focus so much on the leadership issue is because LISA, like it or not, is a bit top-down in terms of how we direct things. So starting with making sure there are people in the leadership of every working group and within LISA as a whole who are diversifying members of the community, who can then tell each working group what needs to be done. And then we can start from there, because something that is very important to say, people working on the instrument in a NASA lab will be very different than people who are more or less freelancing, working on fundamental physics all over the place, and so forth. Kelly? Sure. I think we each have microphones, or do we have to hand them off? Yeah.
Sorry.
Force the habit.
Hello? Hello? Can you hear me?
I mean,
Okay. I don't know if this works. Does this work? Hello. All right. So there are some very specific tasks that I think will be helpful for our community, but one of which, before anything, I think is sort of socializing the concept that this is all of our work and not just, you know, a couple of people in the DEI committee. So just to take seriously the idea that building our community is important to us. And so we're going to make time for it, and everyone is going to try a little bit of something, right? We have such a great pool of folks who are brilliant, and many of us are kind. And so, you know, I think a lot of us can work on these topics. One thing that I wanted to kind of pitch in the context of the consortium, I think it is imperative to sort of land ourselves, start off on the right foot by welcoming people in. And so there are, at least I plan, and many others plan as well, sort of an onboarding process that is incredibly welcoming and makes sure that folks feel as though they belong and have a place in the whole scientific effort. This is a long plan, but if people are interested in helping lower the barrier to participation for new members, then please let me know. There's some very easy things that we can do to start, including things even at this conference. So yeah, let me know.
So Ricardo, then Paula. Introduce yourself as well.
Hi, I'm Ricardo. I'm from Heidelberg, Germany. Just finished my PhD, and so I think there's, as I said, like a whole list of things that people can do. I think from an early career perspective, it's basically important to basically include younger people in many things and just basically try to promote them. I mean, it's kind of like the obvious thing to do, but I think especially if you're new in the collaboration, it can be really overwhelming. There's like so many new things. Maybe LISA is just one of the projects, and it's really important to basically connect them with the people and friend groups. I mean, for example, for me, I participated in the early career scientist school in Les Souches in October last year, and now I'm seeing a lot of people again from the school, and it's very lovely to just basically feel welcome in the community here. So I think the LISA community is already doing a lot of good things, for example, like the mentoring program, that really tries to connect people basically vertically, but basically just pushing this, making people feel seen, especially also if they maybe just don't have like amazing papers out, but for example in CERN there's a lot more with just like general service tracking and these kind of things when you try to make a code base better, these kind of things that are sometimes less visible.
Paula, go ahead.
I think this is a great question, and I actually gave a lot of thought to it before preparing my slides because I really wanted to leave a list for us of topics that we could think about, because I think that especially in the individual actions, there are many things that we can do that are like small, repeated actions that will make people feel included and feel seen and feel heard. So I think they are in their majority not something very hard for us to do, but that sometimes we just don't think about because we don't perceive our own biases, our own behaviors. So I think it's very good if everybody can take a look into the list and think a bit more about it. And in terms of the institutes and collaborations that are like bigger actions that can be taken, or even individually, if you have like a leadership position, like in your department, in some collaboration, or even in your research group, that you can start implementing a few actions to make people feel more welcome. So I won't repeat the topics that I mentioned before. I selected the ones that I find easier to implement and maybe more important, but I think with an effort for all of us individually and also from the institutes on a larger scale, we can do a lot of progress.
Okay, we have some questions from the cards. Do you see one you think is particularly good?
Well, I just received them. Give me a second.
Yeah. Let me give you an example of, I don't know why this has such reverb, of some a DEI relevant situation I was in a little while ago. This is my second big meeting of physicists. The first one, just like a week ago, was to grade the advanced placement physics test. If you've never done this, they call it AP reading. You read the same question 10,000 times and grade it 10,000 times, pretty much. AP, if you don't know, is a program for people in high school to gain college credit by taking a special version of physics class and passing a particularly hard test, okay? So these are people who their decisions will affect how things work for many young people. And they had a really nice function for people who have never done it before. We had dinner, everything was going pretty good. And then they wanted to take a group photo. And someone said, let's do the physics gang sign. This is supposed to be the right-hand rule, and apparently a lot of them know it and call this the physics gang sign. And I did it, oriented like this to the camera, just to make my feelings subtly known. And then I took them to task. You don't call that, we don't call that in Chicago. No black physicist I know, and I know quite a few of them working where I do, calls it that. And I also informed them that if there is an authentically gangland use of physics terminology, does anyone here know what they call somebody who's not in a gang in the streets and even in the prisons? Anybody? A neutron. That's it. You can look it up on the Urban Dictionary if you doubt me, because neutrons, they just go straight through. But if you are in a gang, you might have to turn, kind of like a charged particle versus a neutron. And they came up to me afterwards with many excuses, talking about, oh, well, my students call it that, or I grew up around a lot of black people or whatever, and they're all fine with that or whatever. And these are good-hearted people, but you never know what you do that could be a bit offensive. Now, in fairness to them, I also did talk about a set of slides about establishing a certain committee. I won't say which one, and on the set of slides it said that there will be slight pro-European bias. That's not good. Okay, so we have our own version of that within LISA. There are certain kinds of bias that I've noticed people are just fine with that we need to be a little more careful about. So, yeah. You want to go ahead and read that out?
Yeah.
If you can.
It says, across the issue of DEI, classism in academia remains arguably the steepest obstacle in career success, or longevity, or access to opportunity. As a collaboration, or a community, how can we ensure that financial burdens, like, for example, PhD application costs, conference registration, publication costs, the increasingly skyrocketing cost of living, paired with stagnant wages, are intentionally lessened or eliminated, both in our consortium and our home institutions? For example, CUNY Astro has a mutual aid fund that is run by faculty, as an example, and has helped a student find emergency housing. Yes, this is very similar to Bridge Emergency Fund that I run through this Fisk Vanderbilt Master to PhD Bridge program. You're welcome to donate to that, but it would make sense, for example, if those of us who are from fortunate institutions or have fortunate pocketbooks would be willing to pool their money to help out with something like this. I know that there has been concerted effort here, for example, to help fund students to come to the conference. That's right. So some inroads are being made, not enough, and I think we can do more. Oh, sorry. By the way, if folks are interested in that concept of having a group funded that would be like an emergency fund, let us know and we can set it up.
So you said so the CUNY example, whoever said, was faculty funded, but then you said that people can donate to yours. So is that managed through the university? Is it donor supported? Is it private, like GoFundMe's? Is it something like that, right?
It's kind of like GoFundMe. It's through Zephy, which is a platform that, and honestly, it's mostly a few of us that contribute it every paycheck, but technically anybody could donate it to it, and it might be a nice way to collect and pool funds. It's not going to be a huge amount. I think if we were to want to get a huge amount, we would have to do something like look for grant support or foundation support or donor support. But at least setting up the structure to have a place to accept pooled funds and distribute pooled funds very quickly. It has been, I don't want to be dramatic, but because I keep thinking lifesaver and it's not actually saving anybody's life, but it is definitely making barriers just go away, because sometimes you just need some money.
There's a question online from Stefano Vitale. So he asks about when leadership was referred to, is this leadership within the consortium or on the project side?
All of the above. So we looked mostly for gathering our numbers at the consortium, but anything attached to LISA leadership, any aspect of it, you should think about how you can get a more diverse set of people on board and think about diversity in an expansive way, which sort of relates to the question that I have here from the cards. This individual discusses diversity in terms of the things we don't usually think about, gender, race, nationality, ableness, but people who are particularly short, particularly tall, introverts, maybe people who are not big conference goers, but who, or talk on our weekly or monthly telecon types, can contribute in other ways. And deeply religious people, I would say deeply religious people, if you feel discriminated against for being religious, that's something that is a problem. As long as it's not like, oh, you want to be able to call me a faggot or something. As long as within the Libertarian Party, we have this saying, basically, my freedom begins where yours ends and vice versa. Basically, as long as what you're doing doesn't encroach on anyone else, it should be fine to be as religious as you want. Okay? Or especially, for example, very visibly religious people who are a member of a religion that is also minoritized in the United States, like being a deeply religious Muslim woman, for example. Or for that matter, I know there are some countries in Europe where they cannot wear hijab if they want. That can be an issue for deeply religious people. As for what we can do for them, well, I did my part today by including a couple of deeply, very religious people in my talk, didn't I? So step forward and step up, and we'll see what we can do if you're willing to talk.
AAS has done this. I am a terrible conference goer. It's just way too overwhelming, and I'm such an awkward person. You will find me sometimes going to the restroom in order to just not have to be around people, even though I love y'all. So the AAS has made these little quiet rooms. It's not expensive just to make a quiet room. For religion, that we could make a spot where people need to pray, they can pray without totally leaving the conference, et cetera. So I think just really thinking expansively about what other people need and seeing if there's small things that we can do to implement it. None of that stuff was really hard. All gender bathrooms, sorry. Yeah.
Ricardo, Paula, you got anything to say about that?
Oh yeah, sorry. All gender bathrooms too.
We're having
Let's see. So maybe I missed it, but is there a major difference between diversity of senior and junior members? How can we ensure we don't lose the foundation of people to not getting PhD/postdoc positions? Yeah, that's an interesting thing. I do not have a PhD. I have a master's degree and have taught for a very long time. Maybe there's someone in the room who might help me with that if I didn't already get that space grant funding. I would be somewhere else working on a PhD right now, probably. If you know someone within LISA who does not have a PhD, and you do, and maybe you have room for doctoral students, Well, that's somebody you should think about trying really, really hard to get into your PhD program, right? One thing I seriously considered was going to Vanderbilt to work with you, but part of the reason I didn't was because I knew Illinois was going to stand very strong on LGBT issues and civil rights and whatnot in a way that, well, let's just say it dovetails with one of the historical oppressions we don't usually think about in the United States. I'm ashamed to admit part of it was just a stereotype about Tennessee being Confederacy adjacent. Which that's a real thing. People from the South do face discrimination for their culture. And that's also a real thing that maybe you should think about. But yeah, in short, if you have access to a PhD program and funding for them, encourage them to get their PhD. We have until 2035 to launch, and then hopefully as much time as possible to analyze data. So even if you're old like me, I'm 46, right? That's plenty of time to have a good long career as a physicist. You don't have to be 25 to be a PhD student.
Have we analyzed the sort of demographic breakdown of folks in leadership positions that are from LEX versus not?
I do not think that we have that, though the final data that we have will probably break that out.
Gotcha. That'd be curious. It would be good to know.
As our LEX, our formal LEX liaison, and Paula, as you're also a member of LEX, but also our A&E liaison, I really want to know what you guys think about this.
Yeah, I'm not sure I have anything very concrete to add. I mean, you all probably know that there's many challenges for, I don't know, people who've done their PhD to find postdoc positions, and I mean, the only thing I can encourage to be, I don't know, equitable, or try to be equitable in the selection process. Give people the opportunity to speak in seminars. I mean, as we said before, I mean, some people are not as extrovert as others, so maybe are not as just as inclined to the whole networking game that needs to be done for these kind of positions. So if you see people are interested in the work, maybe also approach them and not just wait for them to come to you, which I mean, it's like the natural vector for these kind of things, but basically trying to encourage them, make them feel welcome, and then they also will probably more likely want to stay in this kind of nice community. And I mean, yeah, there will be a lot of economic barriers. I mean, some people can afford to have a half a year gap in employment between PhDs and postdocs. A lot of people can't, depending on, I don't know, social security nets in the country they have been employed last, and depending on their background. So there's a lot of things to consider and a lot of things that are kind of hard to bridge, but maybe also it would be interesting for some people in the middle to have some kind of, I don't know, internships or like shorter research stays to offer it to them. But yeah, you're probably aware of these things, but just trying to think how you can help would be great.
To add one little bit of data, one thing that supports retention, other than financial, the most is fostering a sense of belonging in a community. And so that is the way that we're going to keep folks who are, especially folks who are underrepresented. So any work that we can do that helps that is going to basically help our community.
Do you have anything to add on this real quick? Paula?
Yes, I think I can talk about how the seniority aspect has been dealt with in the elections that we have in LISA, for instance. So we are making sure that we have enough candidates from the senior election, from the early career election. And it's also important that the early career people do know that they can indeed nominate themselves to be, for instance, early career chairs of working group, and that it's not a position that is made exclusively for people that are already on a senior path. And it's also important to acknowledge how we distinguish between an early career person and a more senior person. For instance, in the example that Hontas gave by herself, that she has a master degree. So is this considered an early career? Is it a senior? So it's something that is we have been discussing in the DEI committee and in the representation that we do for the appointments and elections committee, and we are trying to make sure that young people are also participating and heard, and we also need to pay attention whether they are speaking on meetings, whether they are heard, whether their contributions are taken seriously, and this can be done within each collaborative project and working group.
Okay, to close, I do want to take a look at the word cloud here, and there are many good points made here. Things like, personal kindness, immigration support, mitigating social anxiety, etc. I don't want to minimize those, but many of these things could all be summed up with one word: money. We as a consortium have no money because it's not incorporated that way, but maybe we should collectively think about doing that, finding some way to organize the various financial resources we all have as individuals. After all, we're sitting here in this very nice place, about ready to eat lunch, and had to fly intercontinentally or transcontinentally to be here. We have money, we're not broke. We just need to figure out how to organize the resources we have to better support all levels of LISA membership, and that will help diversify things a lot. Because right now, unless you happened to have the money or the funding to get here, you could not come. For some people, even $180 to be remote was probably a bit of a challenge. To put that $180 in context, I would have to Uber drive in Chicago for an entire day to make enough money so that after my operating expenses, I had the money to pay for that. Okay, that's a lot of work that we're asking for people to exchange for this, especially if you're somebody who's in a position where you just don't have the right kind of job or aren't the right complexion or from the right part of the country, even if you have those things. I hope I've given you all something to think about and a call to action. I want to thank all the panelists. Thank you so much for taking a bit of pressure off me. Let's give them a round of applause. And if you want to think about DEI issues in a more levity-filled way, I recommend that you watch the classic Mel Brooks comedy Blazing Saddles if you haven't.
Okay, thank you. Early careers, your lunch has begun. Please get upstairs to the colony for the early career lunch, and there will be a photograph at the end of lunch for the early careers. So go eat so you can get photographed.
Making everything work, but it worked great. Yeah,
Yeah, hope I didn't get us like
maybe
any CIA agents in the audience are like about to swarm or whatever. Yeah, I think that went very good.
that went really well.